Okay, so how is this? Is this much better? This seems much more responsive from my end. Yes, perfect. Okay. So I took a survey in Discord just to find out what the general impressions that people had on REST API, and so I think it was pretty good feedback on having a supplemental set of lectures just to be able to impress upon just the general and specific concepts for REST, for what a REST API is, how it's defined via HTTP, and I'll actually go a little bit into microservice architecture and how it's actually been enabled by this concept of RESTful APIs. And then I'll pivot over from that to talk about WebSockets, which is what the current lab is that's out right now, and actually how that distinguishes from HTTP in general. Let me jump over here into my my slides. So here we're going to start off with a small slide segment to just talk about REST API and microservices. Perfect. And so here, the kind of basic things that I want to discuss: what is a REST or RESTful API? What are the 6 REST constraints? This concept of how REST and HTTP have been married together, and then we'll just take a quick preview again of HTTP methods and status codes, which we've discussed in previous lectures. Then I want to talk about some of the common wrinkles and exceptions that we might encounter when designing a REST API, which for us, this is pretty important because this is RESTful APIs is essentially what we're building in terms of our backend services to communicate with our front-end services. And so here we'll talk about how the GET method can be abused and how things aren't so self-documented, and how state does matter even though we try for a stateless system. Then we'll talk about what is Microservice Architecture, how it distinguish itself from monolithic systems. We'll talk about advantages and disadvantages of both. And then we'll talk about how RESTful APIs help enable this concept of microservices and how they might manifest themselves in the industry. Excellent. So moving on to just this beginning definition, what is a REST API? Well, let's talk about a web API before we talked about a REST API. So API in general stands for Application Programming Interface. So a web API allows specifically exposed methods of an application to be either accessed or manipulated outside of the program itself. So you want to think, for a web API, you can use some kind of web protocol, whether that is HTTP or XML or JSON or whatever, to be able to send your parameters into a software system and get back a result. So just as you might think of a typical API, like say, for instance, the Java API as one where you see what are the calls you can do inside of your Java system, web API is very similar. It's just you can make these calls across the internet as opposed to actually having to install the application in and of itself to be able to get data back from this from the software package. So you can think of it as a bunch of connected functions, a bunch of functions that you can go ahead and invoke from the internet. So what is a REST API? So REST is short for Representational State Transfer. So that's where we get our R, E, S, and T. It's an awful name. So REST is just a software architecture style. It's a set of rules and conventions for creating web APIs. So the principles of REST are intended to make APIs and systems that are efficient, they are scalable, they are simple, they are reliable, and are modifiable. Okay, so let's talk about what these 6 constraints of REST are, because again, we are now saying that REST is a software architecture that we apply to web APIs, and web APIs are just like normal APIs, but they're public-facing to the internet, or they're internet-facing. So constraint number 1, a client-server architecture. Simply put, REST systems separate the systems responsible for storing and processing the data, so that's going to be your server, from the systems responsible for collecting, requesting, and consuming and presenting the data to the user, so that's your client. So there's a separation of responsibilities between what the server does, and the server's role is just really processing data and storing it, versus the client, which is going to be a lot of presenting data and getting the information, getting input from the user. So this separation could be so distinct that the client and server can be improved and updated independently to each other, which is often the case in web applications. We could actually build these in tandem in isolation from one another. And so we've already seen this conceptually, this concept of having the client side of our application and the server side of our application. So an upgrade to the client should not necessitate an upgrade to the server and vice versa, right? Like we can maintain each piece of this software independent of one another. And that's going to be a powerful concept. Okay, let's talk about constraint number 2 for a REST API. There's the concept of statelessness. So as far as the server is concerned, all client requests are treated equally. There's no special server-side memory of past client activity. The responsibility of managing state, for example, logged in or not, is on the client, and this constraint makes the REST approach scalable. And so what we mean by scalable is if we're constantly getting the information we need from the client to be able to manage requests, then it doesn't matter how many clients we get, it doesn't impact our abilities, the ability of our server, which is going to be the limited resource inside of this kind of hierarchy. So like, for instance, in a server managed state, if you have multiple requests and it's up to the server to manage all the requests, the server could easily get overworked. Whereas if you have multiple clients and each client maintains information related to its request, and the server can easily use what the part of the client's request to service its response. And so a nice thing about this is that it also allows you, if need be, to scale up the number of servers you have to be able to support more client requests. So, and that's how you can bring in this concept of scalability. However, be advised, in REST, each and every resource request is to convey the entire application state. So that means that the state gets transferred with each request. And we pretty much, I think, discussed this topically previously. Let's talk about constraint 3, the concept of cacheability. So clients and servers should be able to cache resource data that changes infrequently. So for example, there are 64 parishes in Louisiana. There are 50 states in the US, right? These are all pieces of data that aren't likely to change anytime soon, not tomorrow or next week or next month. So it's inefficient to build a system that would query a database of states or parishes each and every time you need that data. So it makes more sense that clients should be able to cache that infrequently updated data, and the web server should be able to just control the duration of that cache. I will say that this idea of cacheability can lead to some unexpected developer bugs on your end. So if you've ever run into the case where you've changed like a JavaScript code and you're testing it inside of your browser and you refresh the page, but it's running what looks like an old version of your implementation, it's because it's often the times that the browser will cache your older files. It might not recognize the diff between two different JS files that are getting imported by the HTML. And so this is why sometimes it's useful when you open up your DevTool console for this idea of cacheability when you're actually debugging. When this is open, you can press and hold your refresh button and actually select to empty cache and do a hard reload. So sometimes if you're doing debug work and you can't figure out why your changed code doesn't seem to be taking effect, that could be one of the reasons why, especially if you're using modules, if you're using JavaScript modules, which are imported differently than traditional scripts, JS scripts are, into the browser and executed. Okay. So Constraint number 4 would be the concept of a layered system. And I kind of referred to this, I think, a couple slides ago, where a client cannot tell whether it's connected directly to an end server or to some intermediary server along the way. And so the idea behind intermediary servers is it can help improve your system scalability. Instead of having one server that has to manage all requests, you can actually have a collection of servers that go ahead and manage requests from the users. And then those servers might rely on some core server that maintains the data. So there's one true state of data. But essentially, instead of having that one server have to field all client requests, it just has to field server requests. And you can see how that scales much more nicely in terms of your architecture, in terms of deploying your system. Let's see, the fifth constraint for designing a REST API would be optional one. It's one that's called code of demand. And here it's essentially servers can temporarily extend or customize the functionality of the client by transferring executable code onto the client. And again, this isn't mandatory, but the general concept is that when the client sends a request, it can request for some executable code. So in layman's terms, we can call that a feature, right? So it might request for a feature, and then that feature could be then provided to the client, but not mandatory. Just another way of designing the system. And then the sixth and final constraint would be one that's called the uniform interface. And so the uniform interface is this constraint that's comprised of 4 principles, which I list them down here. But effectively, taken together, these 4 principles require that the API be consistent with HTTP standards and it be self-describing. Effectively, what that means is that given an API web address, a server should respond with all the available actions and resources at that address. Each subsequent server response should then contain enough information to take additional actions on the resource. And again, this is just highlighting what the keyword for this actually is implying. It's designed to provide a uniform interface for any application to be able to make calls to the API. Of course, that means you need to have an identification of resources. That's what our URL is. That's what URIs are, right? You have to be able to have a manipulation of resources through representation, hence the term REST, right? The representational state transfer. You want to think of the hypermedia as the engine of the application state. So we use hypermedia text files. That's the entire idea of what HTML is all about. It's a hypertext markup language for which, as you might know, it can include things like different types of file formats, like images, like JPEG or PNGs or HTML, or it can even be like application/JSON. So all of the MIME types that we looked at when we're looking at web servers define this what the hypermedia spread is. And this all helps us be able to define our application state based off of this media. And then again, the messages should be self-descriptive, and this is why we have methods like get and put and post and delete, right? So the method that we are requesting should be something that is it should be akin to the way you design your software systems, with the way that you define your variables and the way that you define your methods. The same approach you use to build good software in terms of application engineering would be the same way you would for REST API. And this is, in fact, just an extension of what you've already been doing in terms of application development. Okay, so let's talk about this idea of REST API and how it's a marriage between HTTP and this architecture style of REST. So Roy Fielding, who is one of the principal authors of the HTTP specification, also created the REST constraints with HTTP in mind. So I just want to, it's not very often that I bring up names inside my lectures because those are just kind of historical artifacts. But in this particular case, I think it's important simply to understand that both HTTP and REST were designed in unison by the same person. Now, part of the power of the REST architectural style is that HTTP was already widely in use before the REST constraints were formally defined. So in theory, the 6 REST constraints we just talked about could be applied to any other protocols, but in practice, REST APIs are typically HTTP based. And it's again, a big portion of why we've had so much success in implementing REST with HTTP is because it's essentially it was the creation of the same mind. Okay, so let's get back to the HTTP methods. We've covered these on more than one occasions, and we're talking about web clients, we're talking about web servers. We've done several labs that actually have you set up routes to listen on these and to also to go ahead and fetch from these from the browser side. But we'll just, for completeness sake, go over these one more time. So you have the get methods. So the get methods is used to retrieve data from a resource. And according to REST conventions, gets are safe to execute over and over again, right? So you keep getting, and it's not supposed to mutate the state of whatever is being managed on the API side of things. So for example, if it's safe to run the following get requests as many times as you might want. And hey, check it out. I did some research, actually found that there is a DIE API already out there that can roll any kind of DIE that you want. So just to give you a illustration of how it would safe to constantly call this here, I'll go ahead, run this get request. It's going to return a value of 2 on a D6 of on D6. And if we do that again, give me 3, 2, right? 3, 5, yeah. So I could do that again and again, and it won't affect the state of what I'm getting. I'll get some new response. The post method is used to create a data record or to initiate an action. So imagine each post as being a request to, say, for instance, make an Amazon purchase. If that were the case, you would want to be very careful about how many times you do that, right? Because the idea is that you're actually changing the status. You're actually you're committing to something there. You also have put. The put method is used to update an existing data record. And delete is the method that's used to delete a record. So we spent a long time talking about Mongo database operations and how database operations have CRUD operations of create, read, update, and delete. And so notice these methods fit nicely into that same concept. Get is the same as a read method. Post is the same as a create method. Put is the same as an update method. And delete, well, that's the same as a delete method. And then on the back side of things, so these are our requests, right? These come from our clients. Then we have our requests or our responses, which produce back some kind of code. So this lets the client know how the request resulted. And so again, a status code of 200 indicates success. The most common status code is 200, okay. 300 status code indicates that the client needs to do something else to complete the request, right? Usually this means making the request from a different location. Status code 301 means that the resource has been permanently moved somewhere else. 400 status codes indicates a client error. So that is the client sent the request that did not make any sense. An example of that is a 404 not found error. That means that you sent a request for a route that doesn't have anything added, that isn't being listened to. And then a 500 status code indicates a server error. So notice we use these the same way you would use status codes inside of an application. It's just these are communicated between the client side and the server side of the application layers. And so a 500 status code indicates service error. That means that the request made by the client appears to be fine, but the server is experiencing some kind of difficulty. So an example for this would be like a 500 internal server error. So let's talk about some common wrinkles and exceptions that might occur when you're going for a REST API, designing a REST API. The REST design constraints, they're good in theory. However, in practice, no one, not even the largest technology companies, implement them perfectly. And 3 of the most common constraint violations are followed. The abuse of the get method. And I'll be honest, I abused the get method in our high-low game for testing purposes, because it's easy for you to test Git methods by just copying the route into your browser address bar and refreshing it, just going to it and seeing what the JSON response is. So since that was our first attempt at building a REST API via lab, I am certainly guilty of having you do this. So we've already all done this first violation. So we'll talk about that. Some other ones are APIs that are not self-documenting. This is an easy thing to try to avoid. Just adhere to the same kind of rules you learned in Java 1 and Java 2. Try to produce routes that indicate what it is they will result back from. And then finally, state does matter often is for most applications. And honestly, we can't get away from this. This is actually just something we have to deal with, but it is a wrinkle in terms of true RESTful design. Okay, so let's talk about some of these abuses of the Git method. So Git is assumed to be a safe operation, as I said before. And I showed you with the DICE API, where I keep rolling it again and again and again. And it should never really affect anything because it never modifies the state of the resource, right? It's just generating a new die role. However, it has been often contorted to perform other functions. And one reason why that's the case is because it's so easy to just send Git requests, right? It's a little bit more difficult to send things like put or post or delete requests from the browser side because we have to wrap it into a fetch. But that is the more appropriate way to do it. And so I'll give you an actual example of one of the APIs that actually provide to you as a resource, the Deck of Cards API. That uses a Git endpoint that actually draws a card from the deck. So if I go to I can't actually, I don't have the deck ID, but if I generate a deck of cards with Deck of Cards API and then use Git and tell it to draw 2 cards for me, it's actually mutating the state of my deck, right? That's more like a put request, right? To update the state of something that now exists. But I'm using a Git for that, and this conceptually violates one of the principles, because this isn't safe, right? If I keep calling this method again or if I keep calling this a URL, or essentially hitting this API endpoint again and again and again, I'm going to run out of cards. It's not safe to perform indefinitely. It's actually mutating the state of my deck. Does this make sense, what I'm saying here, to everybody? How we could abuse this Git method? How this would be a violation of the concept of what Git means? Okay, good. Okay, so let's talk about APIs that are not self-documented. The REST ideal is often ignored, right? So what we just talked about. Conceptually, the principle behind it is the same for defining variables and methods with meaningful names. So again, just rely on your training for how you produce self-documenting code. Is that a term that everyone's encountered when they went through Java 1? Self-documenting code, create variables that have meaningful names, create functions that have meaningful names by producing a code base where everything is intelligently designed. You can read it as if it were pseudocode. You can read and understand the logic without even having to need comments for it. And so we will strive for those same type of naming schemes when we design our REST APIs. And then finally, state matters. So in the REST design, the burden of managing state is on the client, right? So that, however, raises many security concerns. We talked about this in the user authentication lectures. And so actually, we opted to actually have some kind of server-side management, but the client is still responsible for giving us information. It's giving us the essentially the cookie to be able to properly service the request. So the HTTP itself is still stateless. Anyway, API providers like the efficiency gains made by this concept of REST, but there is no one consistent approach for managing state. And this is exactly why in the user authentication lecture, we talked about both handling sessions via cookies and handling them via tokens, where one approach is to have the client maintain all the data, whereas an alternate approach is the client maintains essentially a key that unlocks their data on the server side. And so again, both these approaches are equally used in industry. There is no right way to do this. And because of that, this has created kind of a difficulty when it comes to REST design. There's no one way to manage this concept of how you're going to have a statefulness to be able to handle the same client again and again. Okay, so that's it for the most part with REST API. So the idea behind a REST API is you can think of it as the same as building a library or a module of code as if it were in Java, but all the way with having documentation describing what the collection of methods does. But instead of these methods being exposed to other Java-like classes, you're exposing these method invocations. They can be invoked from URL routes, right? By hitting a route on a web server, will invoke as that endpoint that function that processes some data and then returns back a result, typically as a JSON, to whatever requested that data, which is typically a web client. So when I break the concept down to that, does a REST API make sense to everybody? It's just an API, just like it would be for any other software system. It's just exposed publicly on the internet so that your client code can actually come from networked request. Now that's all a REST API is. But one reason, so REST API have become immensely popular in industry. A lot of the work that you'll likely see done is designing REST API or REST clients that consume REST APIs. And I should say that you can have a web server that is also a client. Like a web server can send fetches to other servers to request data for its own processing. So servers, there's not necessarily where a web server is only a server. A web server can also be a client in some aspects. And this is what brings us actually to the concept of microservices. And one reason why microservices has become a popular architecture approach in terms of web development and application design with networked applications. So let's talk a little bit about microservices so we know what we mean when we're talking about that. And actually, let's compare them to the more traditional monolithic architecture, which is what you've learned how to do probably in all of your programming classes. So what is a monolithic architecture? Well, monolithic means it's composed all in just one piece, right? So the monolithic application describes a single-tiered software application in which different components combine into a single program from a single platform. So an example of, say, for instance, an e-commerce application in a monolithic architecture might look like this. You have a combination of what your logic might be, like your payment services, your order services, your catalog services, but all of this different logic exists within the same application and executes on the same machine and the same environment. And so you might then get a request where then takes that request and then processes it through all the different portions of what this application's designed to do. And again, think about your traditional Java applications you might have made in Java 1 or Java 2. Those are also monolithic architectures where all of your classes interoperate together with one main, right? And that one main method will then coordinate all of the classes together to produce whatever the unified result is. So your application you can think of as a uniform piece of technology. It's homogenized together. Okay, so what are the benefits of this monolithic architecture? And again, this is probably the base way that all developers initially start creating code. Well, it's simple to develop using the monolithic architecture. At the beginning of a project, it's so much easier just to start putting all of your source code together to be able to start doing whatever the task at hand is. It's simple to test. For example, you can implement an end-to-end testing by simply launching the application and then testing the user interface, say with Selenium, or say, for instance, you could do JUnit testing if you're doing a Java application. Or you could just run the application and test it out yourself, right? Like you could put in some console logging or interface it with some kind of either text user interface or some kind of graphic user interface, and just test it. It's simple to deploy. You have the code packaged as an application to the server, and it's simple to scale horizontally by running multiple copies of the same application across a load balancer. We won't get too much into load balancers. Okay. So what are some of the drawbacks of a traditional monolithic architecture? Well, maintenance. This is the really biggest thing between microservices and monolithic, is when it comes to after you deploy your services and when you have to go into maintenance mode, which is the longest duration of any software application, right? Typically, the shortest time will be in the development cycle, ideation, design, development cycle, all the way to get to deployment, and then you get into a maintenance mode, and it'll be in maintenance mode all the way until it hits an end of life cycle. And so if you go into software engineering, I'm sure you already have covered like software design life cycles, but that's pretty much it in a like 3 sentences. You've probably already encountered the life cycle, even just going through a course. But if your application mainly exists in a maintenance mode, this is actually where the most difficulty comes in this kind of architecture. If the application is too large and complex to understand entirely, it becomes incredibly challenging to make changes that are both correct and that are fast. Some other complications you can have, typically also because of maintenance, is the size of the application can slow down the startup time. You have to redeploy your entire application every time you update it. So a lot of times with web applications, downtime is very much a big issue, especially if it's a REST API that's servicing a lot of other requests. You want to minimize the amount of downtime, especially if you have to make a small change to one part of the system. The fact that your entire system has to come down it can be quite painful. Let's see, monolithic applications can also be challenging to scale when different modules have conflicting resource requirements. You can have issues with reliability. So a bug in any module can potentially bring down the entire process. And regardless of how easy the initial stages may seem, monolithic applications have difficulty adopting new and advanced technologies. And this is because a monolithic architecture is reliant on being on typically the same technology stack, or it's dependent on the technology stack that it was built around. So it becomes very brittle, and it becomes very reliant on how it was initially designed. So let's say 2 years down the line, let's say that there's a new language that emerges that becomes very powerful in one aspect of what your application does. Let's say it's data processing. Let's say it's scientific data processing. Let's say all of a sudden Python has this new module that you were previously relying on the R language to do. It becomes incredibly difficult to be able to adopt towards that new technology in a monolithic architecture. So you're kind of married to your initial design. So let's distinguish that from microservice architecture. So in general, what a microservice architecture means is that you have microservices that are just structures an application as a collection of services. And these collection of services, they're designed to be highly maintainable and testable. They're loosely coupled. They're independently deployable, and they're organized around whatever the requirements are for that tiny little service. So let's look at that same application hierarchy using a microservice approach. So here we might have like our online shopping service. And so then it distributes all of those roles that it was conducting through a monolithic architecture by actually isolating them as tiny deployed services. So you might just have like the catalog service, which maintains its own database, and the cart service, which maintains its own database, and the order service that just maintains its own little database, and the payment service that maintains its database. And so, for instance, the payment service might have to then communicate with the cart service to be able to process what it has to do payments for. So you can have, like, again, these services can intercommunicate just like it would in a monolithic architecture, but they communicate the same way that anything else would in conceptually as like you would with a REST API, right? So so they're designed to be autonomous and independent from one another, but they can still cross communicate through the same facilities that you send requests and get responses from. And so let's talk about some benefits of this microservice architecture. So microservices, they enable continuous delivery and deployment of large complex applications. And continuous delivery in this instance means that you can deploy tiny portions of the service along the way, right? You don't have to wait until the entire application is built. You can create an MVP build that's built from a tightly created set of your microservices and then expand them out as you continually add more and more features. It provides even better testability because the services are small and they're faster to test, right? It's not part of a larger monolithic application. The role and size of each of these services is diminished. There's better deployability. The service can be deployed independently of the rest of the application. So notice this is also going to make maintainability much easier. You only have to maintain a collection of microservices. If there's a bug with one microservice, you can pull it down without disrupting the other microservices. If there is a new technology or a new language module or framework or library that you would like to adopt into your technology stack, you can pull the relevant microservice down and refactor it and redeploy it without having to bring the rest of the system down or redesign the rest of your system. So you can see this concept of having like these little data processors self-communicate, create a more modular application design, something more like a Lego system, as opposed to something that's more welded together. However, that does come with some drawbacks, right? It's more complicated to initially design a microservice application. And that's because where you could just directly access the classes and methods in a monolithic structure, you actually have the overhead of coordinating the communication through something like a more formalized API, like a more formalized REST API structure, where you have to manage listening for requests and responding to those requests to whatever the service is. So there is that overhead of intercommunication between what would commonly be a simple function call. So there is the complication in your initial design, but the maintainability it provides thereafter is supposed to be the big gain. Okay. And so I just want to highlight that REST enables microservices because microservice architecture has become so increasingly more popular due to the advent of REST APIs. And it's not a coincidence that microservice architecture for applications became more popular when web APIs have also become more popular. And that's because the architectural style of REST has enabled microservices to become a thing. The REST constraints we talked about provide a strategy, an actual implementable strategy to easily isolate your system components into their own APIs, thereby becoming a microservice. And so there's actually, I've seen many companies, even in the local areas such as Lucid, who have taken their monolithic software designs and stripped them apart and refactored them into a microservice architecture. So I figured while we're talking about REST, I'd also talk about why you might hear microservice architecture and why the concept of REST might marry into microservice architecture and why HTTP marries into REST. So with that said, that's my quick little crash course on just like REST design, REST constraints, what it means to be a RESTful API, and what it means to be a microservice versus a monolithic architecture. Do all these concepts for the most part make sense? Is there any questions about this? Or has this made it more clear in terms of what we had done with the labs, especially labs 10 and 11, where we made a REST API in the form of the high-low game, and then we built a REST client that then sends requests to the REST API to actually implement a game off of that API. Did this help elucidate or enlighten or crystallize those concepts for you?